In this section, we are going to discuss about Minkowski's inequality. നമ്മൾ ഹോൾഡേഴ്സ് ഇനീക്വാളിറ്റി പഠിച്ചിരുന്നു. അപ്പോൾ ഫംഗ്ഷൻ ആക്സിസിൽ തന്നെ ഉള്ള അനദർ ഇമ്പോർട്ടൻറ്റ് ഒരു ഇനീക്വാളിറ്റിയാണ് Minkowski's inequality. So let us see. Actually, Minkowski inequality എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ട്രയാങ്കുലർ ഇനീക്വാലിറ്റിനെ തന്നെയാണ് Minkowski inequality എന്ന് പറയുന്നത് for LP space. LPN means for in Rn. If it is sequence, we have infinite sequence, we have LP, right? So let us see what is this. For every sequence A, sequence AI and sequence BI with 1 less than or equal to P less than or equal to infinity, what we have is norm of A plus B is less than or equal to norm A plus norm P with respect to P norm. Okay, so what is this actually? Clearly the triangle inequality, right? Norm of X plus Y is less than or equal to norm X plus norm Y. So this is Minkowski's inequality. Okay, let us see how we will prove. First case, we have 1 less than or equal to P less than or equal to infinity. Aditya case, let's suppose P equal to 1. So P equal to 1 means 1 norm, right? So how will define the 1 norm? You know that norm A plus B 1 norm is equal to sigma I equal to 1 to infinity modulus of AI plus BI, okay, which is less than or equal to. So you can apply triangle inequality for modulus. So we have less than or equal to sigma I equal to 1 to infinity mod AI plus mod BI, which is equal to, since both are positive, you can directly equality whole sigma I equal to 1 to mod AI plus sigma I equal to 1 to mod BI, which is equal to norm 1 plus norm A plus norm B, okay, with respect to 1 norm. So clearly it holds for P equal to 1. This is a trivial case actually, right? Okay, next, when P equal to infinity. So what P equal to infinity means sup norm. You are having sup norm. So what is sup norm? You know that, okay? Norm, sup norm is equal to A plus B is equal to supremum of modulus of AI plus BI, right? Which I equal to 1 to 3, but we can apply the triangle inside. So we have less than or equal to supremum of mod AI plus mod BI, where I equal to 1 to 3, etc., right? Which is equal to supremum of modulus of AI etc. plus supremum of mod BI. Okay, so it holds trivially for also for sup norm, right? Okay, so now the non-trivial case, okay, that is 1 less than P less than infinity. So what happens? Let's see. Norm of A plus B, pth norm. So you can define, right? Sigma k equal to 1 to infinity modulus of AK plus BK raised to P whole raised to 1 by P. Okay, now you take the pth power. So what do you have? Norm of A plus B raised to P is equal to k equal to 1 to infinity modulus of AK plus BK whole raised to P. So whole raised to PP, it will becomes 1, right? Okay, which is equal to, ഇതിനെ സെപ്പറേറ്റ് ചെയ്ത് എഴുതാൻ പോകും. P minus 1 1 ആയിട്ട് എഴുതാൻ പോവാണ്. പവേഴ്സിനെ സെപ്പറേറ്റ് ചെയ്യണം. So we have modulus of AK plus BK raised to P minus 1 and another term mod AK plus BK, and which is less than or equal to, we are applying the triangle inequality for this term. So we have less than or equal to sigma k equal to 1 to infinity modulus of AK plus BK raised to P minus 1 into mod of AK plus mod BK. Okay, so now you are using distributive law. So we have which is equal to sigma k equal to 1 to infinity modulus of AK plus BK raised to P minus 1 into mod AK plus sigma k equal to 1 to infinity modulus of AK plus BK raised to P minus 1 mod BK. Okay, now what we are going to do is, you know this term, right? So it's optimum AK into BK, sigma AK BK. So we are applying holders inequality for each term. Okay, so what happens? Let's see. So when you apply holders inequality, we have less than or equal to sigma mod AK plus BK raised to P minus 1. So whole raised to Q and this raised to Q whole raised to 1 by Q. Okay, into sigma AK mod AK raised to P whole raised to 1 by P plus the second term also sigma mod AK plus BK raised to P minus 1 ഉള്ളിലുള്ള ആൾക്ക് raised to Q, പുറത്തുള്ള all എല്ലാവരും കൂടി ചേർത്ത് 1 by 2 into sigma mod BK raised to P whole raised to 1 by P. Okay, now what we have is p minus 1 into q is equal to p. You can get from 1 by, since p and q are conjugate pairs, okay, fractional conjugates, we have 1 by p plus 1 by q is equal to 1. From this you will get like this, right? We have discussed like that before. Okay, so what we are having is p minus 1 into q will be equal to p. So when you substitute that, what we will have is sigma mod ak plus bk raised to p whole raised to 1 by q into this one adepole thanne edi plus this will again p minus 1 into q can be written as p raised to 1 by q into sigma mod ak raised to p whole raised to 1 by p. Okay, so again, so what you have is e term common ആയിട്ടുണ്ട് അതിനെ പുറത്തെടുത്തു. So we have sigma mod ak plus bk raised to p whole raised to 1 by q പുറത്തെടുത്തു. What you have is sigma mod ak raised to p whole raised to 1 by p plus sigma mod bk raised to p whole raised to 1 by p. Okay, ഈ ടേമിനെ ലെഫ്റ്റ് സൈഡിലേക്ക് കൊണ്ടുപോയി. അവിടെ ഇങ്ങനത്തെ ഒരു ടേം ഉണ്ടായിരുന്നു. സോ വി ഹാവ് 1, ഇറ്റ് വിൽ ബി 1 minus 1 by q which is less than or equal to, this term is actually pth norm, right? So norm a plus norm b under pth norm. So this one what you have 1 minus 1 by q. 1 minus 1 by q means 1 by p, right? So what we are getting sigma mod ak plus bk raised to p whole raised to 1 by p. So that is pth norm. So norm of a plus b less than or equal to norm a plus norm b. So we have proved the result. Okay. Okay, next. So integral, next is integral form of Minkowski's inequality. Okay, so it's for 1 less than p less than infinity. You have to see this, which is not equal to p equal to 1. Okay, p equal to infinity. Just for 1 less than p less than infinity, the function closed interval a comma b, this integral and integrate to be mod f of x raised to p dx and integrate to be mod g of x raised to p dx etc. in the sense of Riemann integral. Okay, so and again this integral is also exist അങ്ങനെയാണെങ്കിൽ which satisfies integrate to be mod f of x plus g of x raised to p dx whole raised to 1 by p is less than or equal to the first term integrate to be f of x raised to p dx whole raised to 1 by p plus integrate to be g of mod g of x raised to p dx whole raised to 1 by p. Okay, so in this is the integral form of Minkowski's inequality. So let us see. So we know that for the Riemann integral we will partition, right? So we have, let's suppose the partition is a equal to x0 comma x1 comma etc xn which is equal to b device closed in the a comma b. Okay, so of n intervals, equal intervals. Okay, so then this sub interval length delta x equal to b minus a by n. Okay, so now you consider this term and inside term, so sum term sigma equal to 1 to n mod f of xi plus g of xi raised to p delta x whole raised to 1 by p. So this is the Minkowski inequality apply cheyam for the sum case, right? Discrete sum. So what you have is which is clearly less than or equal to sigma equal to 1 to n, the first step mod f of xi raised to p delta x whole raised to 1 by p plus sigma equal to 1 to n mod g of xi raised to p delta x whole raised to 1 by p. Okay, so if the Riemann integral we need this delta x, the norm tends to 0, that is delta x tends to 0. Delta x tends to 0 means we need n tends to infinity, right? So letting n tends to infinity, this left side becomes the integral and all these things becomes integral. Okay, so hence the proof. So this is very easy proof for integral. We are using the Minkowski for discrete case to prove this. Okay, now so let us try these two exercises. Assignment 1, what you have to do is for n greater than 1, നമ്മൾ പറഞ്ഞത് 1 less than or equal to p less than or equal to infinity ആണ് Minkowski's inequality പറഞ്ഞു. So what happens when in between 0 less than p less than 1? Is it a no? ഇതൊരു p norm ആവോ? That is what I am asking. നിങ്ങളുടെ ഉത്തരം എന്താണെന്ന് നോക്കുക. Why? എന്തുകൊണ്ടാണ് explain ചെയ്യും. Okay, and next case, show that for 1 less than or equal to p less than r less than infinity, LP is the sequence space. LP is a proper subspace of LR. This is known as Jensen's inequality. Actually, you try. It's very easy to prove. Try these two problems. Okay, thank you.